Rolling motion is one of the most common types of motion we observe in everyday life. From wheels on vehicles to balls rolling down slopes, this phenomenon combines two fundamental types of motion into one elegant system. Today, we'll explore how translation and rotation work together to create rolling motion. Rolling motion occurs when an object experiences simultaneous translation and rotation about its center of mass. This means the object is moving forward in a straight line while also spinning around its own center. Think of a bicycle wheel. As the bike moves forward, the wheel rotates. Both motions happen at the same time, and they're perfectly coordinated. Rolling motion can be broken down into two distinct components. First, there's translation, which is the linear motion of the center of mass. This is the forward movement of the object as a whole. Second, there's rotation, which is the angular motion about the center of mass. This is the spinning action around the object's central axis. Both components must work together for proper rolling to occur. For an object to roll without slipping, a very specific condition must be satisfied. The linear velocity equals angular velocity times radius, or v equals omega r. This relationship ensures that the point of contact with the ground has zero velocity. When this condition is met, the object rolls smoothly without any sliding or skidding at the contact point. Different points on a rolling object have different velocities. At the top of the wheel, the velocity is 2 times v, which is twice the velocity of the center of mass. At the center of mass itself, the velocity is simply v. Most interestingly, at the bottom where the wheel contacts the ground, the velocity is 0. This zero velocity at the contact point is what distinguishes rolling from sliding. The total kinetic energy of a rolling object has two parts. The formula is KE equals 1/2 mv squared plus 1/2 I omega squared. The first term, 1/2 mv squared, represents the translational kinetic energy from the linear motion. The second term, 1/2 I omega squared, represents the rotational kinetic energy from the spinning motion. Both must be considered to find the total energy. We can simplify the kinetic energy expression by using the rolling condition v equals omega r when we substitute omega equals v divided by r into our energy equation. We get KE equals 1/2 mv squared times the quantity 1 plus I divided by mr squared. This form makes it easier to calculate the total kinetic energy using just the linear velocity and the moment of inertia. Let's review the key concepts. First, rolling combines linear and rotational motion in a coordinated way. Second, the contact point has zero instantaneous velocity when rolling without slipping. Third, total energy includes both translational and rotational kinetic energy components. And fourth, the rolling condition v equals omega r must be satisfied for motion without slipping. Understanding these principles is essential for analyzing rolling motion in physics.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.